This is an image file containing a picture of my cat. But if I rename it to .mp4, it becomes a video file, also of my cat. If renamed to .pdf, it becomes a text document containing the script for this video. It can also be a valid web page, a zip archive, or a PowerPoint presentation, all by simply changing the name. This kind of file is sometimes called a polyglot, although usually that term refers to code that works in multiple programming languages, hence the name, polyglot. Of course, text is one thing. Storing media this way is a lot more interesting. Computers store data in long strings of ones and zeros. You probably already knew that. You might also know that those ones and zeros are just numbers. Therefore, an image is just a grid of those numbers. But if that's the case, then how do we know to arrange these numbers? What decides the dimensions of the image, or the quality? Naturally, you might think to just add a few more numbers, separate from the image data. For example, the width and height to set the dimensions, and bits per pixel to define color depth. We might also want to include the source of the image, the date on which it was created, and some other metadata. And to make sure that we don't confuse this with some other image format, let's add a so-called magic number to the start, which is unique to this type of file. This structure is called a header because it often appears at the top of the file. Almost every file has one, and it's what programs use to determine what to do with the data. The file extension, the part after the dot in the file name, is only used to determine what program to use, and not what that program does. For example, renaming a PNG file to .jpeg probably won't break anything, because both of them request your default image viewer, which ignores the file name and simply refers to the headers. But if our goal is to bundle different types of media, such as an image and a video, into the same file, then this becomes a problem. We need a file that can imitate both a video and an image, depending on which program is reading it. The data blobs can just be stacked on top of one another, but the headers have to be at the very start, which means that we have to merge them together. If you try to do this with most media files, you'll find that it's just plain impossible. For example, a PNG starts with hex 89, followed by letters PNG, and a GIF starts with the text GIF89A. These have to be the first characters in the file, so obviously there's no way to merge these headers. A rare few file formats, like TrueVision TGA images, have a very loose header structure, without a magic number. This is usually because they're tied to specific hardware. In this case, TGA was a specialized format for the first ever true color graphics cards for IBM compatibles. Let's take a look at this format. The first byte defines the size of a metadata block, so it can basically be anything. The second byte is either 0 or 1, depending on whether the image uses a color map. The third byte picks the image type, and can theoretically be any number from 1 to 3 or 9 to 11, and in some cases even 32 and 33. And the next 5 bytes outline the color map, but if you're not using one, you can fill these with pretty much anything. With this, I was able to create a polyglot out of a TGA image and an MP4 video. The video component worked fine, but the image had to have a very low resolution for this to work. On top of that, TGA is an incredibly old and bespoke format with limited software support. I wanted to try something more mainstream, but for that, we'll first have to take a closer look at the MP4 header. Now, technically, MP4 doesn't have a header. Instead, it uses these boxes called atoms to modularly define data. However, most video players expect the FTYP atom, the file type atom, to come first. This atom is split up into 4-byte chunks. The first 4 bytes encode the size of the atom, and the next 4 bytes contain the name. In this case, that's just the letters FTYP. That's actually how I was able to make the TGA polyglot. These letters happen to land in the color map field that I wasn't using. If you're confused about the sudden appearance of letters, don't be. They're still just numbers under the hood, mapped to a table that works kind of like a digital alphabet. Anyway, next comes the major brand name, which defines what specification this file follows. For MP4, that's usually ISO-M, which stands for ISO media. It doesn't necessarily imply an MP4 though. The next 4 bytes encode a version number, and the following chunks list all supported brands, including MP4-1. that's the first and only mention of this file actually being an MP4, specifically version 1 of the spec. Now, after a bit of experimentation, I found that most players don't actually care about what's in this atom. They just need it to come first. In fact, they often don't even check if the first atom is called FTYP. They just assume that the first atom has to be the file type. Well, all but VLC. It does care and will simply refuse to play the file if the FTYP name doesn't appear in the first 256 bytes. Still though, in most other cases, this atom is a header sandbox. However, you do still have to be careful. Those first 4 bytes that encode the size make up an unsigned 32-bit value, which can go up to 4 gigabytes. While that's not a technical limitation, it can be a very real logistical problem. Because of this, we can't just plug in a PNG header. That would bloat the file to about 2 gigabytes. JPEG would be 4 gigabytes and GIF would still be over a gigabyte. Pretty much every mainstream image format has a complicated magic number that gets really big when parsed as, well, an actual number. Once again, that's why TGA worked. It doesn't have a magic number. Its header can start with a bunch of zeros. But this really seems like a lucky coincidence that doesn't pop up in any other image file. Well, except for one. The Windows icon has an incredibly generic header. Its 4-byte hex signature is, I kid you not, 00000100. Better yet, it allows you to offset the actual image data to anywhere in the file. Let's align this to the MP4 header. The first 4 bytes are that super generic signature, which translates to a 256-byte atom size. For now, that just means we have to extend the supported brands list with 240 bytes of empty data, which will become important later on. The next 2 bytes specify the amount of images that the icon holds. In our case, let that be just 1. The next 8 or so bytes define the parameters of the image, but we can pretty much just ignore these. The thing is, Windows icons support bitmaps and PNG files. And if you're using a PNG, these parameters are often inferred from the PNG data. So really, the only data that we have to consider are the last 8 bytes, which tell the icon where to find that PNG. This begs the question, where do we put the image? As I mentioned earlier, you can often just stack blobs of data on top of each other as long as the headers know where to look. But if we want to be a bit more careful, we can embed the image into the MP4 itself. Among the many MP4 atoms, there are a few that are reserved for ancillary metadata. The skip atom does exactly that. It skips any data that it contains. We can safely put the entire image in here, and the MP4 will just ignore it. Remember, if we just did this without the header jank, it wouldn't be enough to combine a video and an image, because the software that actually reads the data won't know where to look for it without our Frankenstein header. So with this, we've built a 2-part media polyglot. It can be an MP4 video or a PNG image. Now, hold on, I said this used a Windows icon, didn't I? That should use the .ico extension, but here PNG works just as well. Once again, this is because the file name is only used to invoke the right program. For MP4, that's a video player. For ICO and PNG, that's an image viewer. The program itself doesn't actually care about the file name. It just reads the header, sees that it's a Windows icon, and parses it as such. Anyway, the logical next step is to continue cramming more file types into our polyglot. And for that, let's first take a look at some low-hanging fruit. Unlike most files, zip archives are actually read from the bottom up. This is because, back in the days of floppy disks, it wouldn't be uncommon for a zip file to span multiple floppies. Most computers only had 1 or maybe 2 disk drives, so it would have been very inconvenient to swap between disks and rewriting the whole archive just to add 1 file. Because of this, zip files don't have a header per se. Instead, the central directory, as it's called, is simply appended to the end of the file. For 1989, this meant only having to insert the last floppy disk when adding a file. For 2025, this means we can literally just copy-paste a zip file to the bottom of our polyglot, and it'll mostly work as expected. However, if we leave it as is, most tools won't be happy. The Unix unzip utility does extract the files, albeit with a scary looking warning. This can be mostly remedied by applying an offset fix, typically meant for self-extracting archives, though some programs may still naively assume that a modern-day zip is safe to read from the top down. Interestingly, there are actually a whole bunch of file formats that use a zip file under the hood. For example, if you rename a modern PowerPoint presentation to end in .zip, you'll see that it really is just a zip file in disguise. The same goes for Java applications, Android APK files, and many other packaged files. Another relatively simple addition is PDF. If you take a look inside of a simple PDF file, you'll see that it's mostly just plain text. This is because a PDF is really just a form of markup, similar to code in a programming language. And, as I said earlier, making polyglots of code is usually not that difficult. PDFs do have a header, but because it's semantically just a code comment, most PDF readers don't require it to be at the top of the file. As long as it's somewhere in the first kilobyte or so, they'll often let it slide. We just need to find a bit of space somewhere near the top of the file. This is where those 240 bytes of empty atom data come into play. See, I told you it would be important later. Now, 240 bytes is not a lot. It's definitely not enough to store the whole document, but we can at least fit that header. Then we can declare a PDF object, assigning it the size of the entire polyglot file. To the reader, this now looks like valid PDF data. It doesn't actually matter what's inside of this object, as long as it's never used. And finally, at the end of our polyglot, we can close that object declaration and tack on the real PDF data. This is already enough to satisfy every PDF reader I've tested, but just to be thorough, there's one more thing we can do. Every PDF file has a cross-reference table containing exact byte addresses to all the objects in the document. This makes jumping between large chunks of data much more efficient. But since our PDF now has a bunch of garbage on top of it, these addresses are going to be offset. Again, most PDF readers won't really care, but just to be nice, we'll adjust these too to point to the correct locations. At this point, our polyglot is starting to get really cramped. I can only really think of one more freebie before things get complicated, and that's HTML. This is the stuff that holds together the structure of nearly every single website. As a standalone file, it can be used to serve a local copy of a web page. Yes, technically this is code, but it's the kind of user-facing code that you don't really think of as code. Still, it does retain the property of being really easy to embed. We can quite literally just jam it into another skip atom in the middle of our MP4, and it will remain mostly coherent. HTML is incredibly noise-tolerant, in the sense that it's happy to interpret noise as valid data. To fix this, I wrote a small style sheet that sets the font size of the entire document to 0, except for the parts that I want to display. You can even use this to embed any arbitrary media, like a picture of my cat, by converting it to base64 text and providing that as a URL. The final piece that's missing from our all-in-one media polyglot is an audio file. Sure, you can put an MP3 in the zip archive or embed audio into the HTML webpage, and yes, technically the video file already has audio, but I'm talking about a dedicated audio file format. As per usual, most mainstream audio formats have strict header signatures, with magic numbers and exact byte ranges. Ironically though, the most mainstream of them all, MP3 files are pretty much the only ones without a strict header. MP3 audio is split up into hundreds of chunks, each only a few milliseconds long. These chunks each have their own 4-byte header, and the file format is designed to detect and withstand any surrounding noise. Just like with zip files, you can literally just append an MP3 file to the end of the polyglot, and it'll still count as a valid MP3. However, in reality, there's a very silly problem with this approach. You see, most modern media players support playing back video and audio files, all in the same program. Nowadays, there are hardly any dedicated audio-only or video-only programs. And, as I said, the programs that we do have rarely check the file name. So, when a media player reads my polyglot, it encounters the video data first, and starts playing back the video before it even notices the MP3 data. The only media player that successfully plays back the MP3 is VLC, and that's probably just because it can't recognize the MP4 data. I tried a few more obscure approaches like Amiga soundtracker songs or other ISO media files, but the header is simply too cramped to fit anything else. At one point, I got really close to embedding a Windows Media download package, which is basically just a zip file that contains a playlist, a skin, and, crucially, audio for the Windows Media Player. But because this is an obscure and long-deprecated feature, the zip support isn't good enough to handle a polyglot. Let me know if you've got an idea on how to cram audio into this thing. In the meanwhile, do check out the description. I'll leave a link to a polyglot file for you to try out with various media of my cat, along with a link to this project on GitHub. This whole thing culminates in a tool I made that can generate polyglots from any of the files that I talked about. If you want more esoteric comp-sci jank, you should subscribe to the channel, or you can check out my last video about playing Doom in a Discord GIF. YouTube took it down for a week, so its viewership is terrible, but it's otherwise a pretty good video. Anyway, that's all from me today. See ya!